and up, and away we go. So, there is a warm-up. Tracing some recursion. You want to do it together? Okay. Let's share some pain here. All right. Let's evaluate these. Homer of 9. Here's function Homer, so I'm going to draw my little box diagram. Homer of 9 gets called first. If 9 is less than or equal to 1, not true. So I'm going to call Homer of 9 divided by 2, which is 4, integer division. And then eventually it will print comma n. So I'm going to do plus comma 9. I'm going to treat that like what do we talk about? Treating it like concatenation. Then I got to evaluate h of 4, Homer of 4, because I don't know it. I'm not going to write Homer every time, because I don't have time. I got 2.5 minutes to do every question here. Homer of 4. 4 is not less than or equal to 1, so I'm going to call Homer of 2. 4 divided by 2 is 2, last time I checked. And then I'll do plus comma 4. Remember, this comma 4 won't print until h of 2 is done. This comma 9 won't print until h of 4 is done until h of 2 is done. So now we got to figure out what h of 2 is. All right, let's see. H of 2. 2 is not less than or equal to 1, so I'm going to evaluate h of 1 plus comma 2, which will print some point. And then I got to figure out what h of 1 is. What is h of 1? Let's see. 1 is less than or equal to 1, so it's just going to print a 1. Now I'm going to treat the rest of these as concatenation as I go down. Here we go. I'll even change colors to show it. H of 1 printed out 1 plus comma 2. 1 comma 2. H of 2 printed out 1 comma 2. So now I added on to this comma 4. 1 comma 2 comma 4. H of 4 printed out 1 comma 2 comma 4. And then we tack on that comma 9, so we get 1 comma 2 comma 4 comma 9, and that is our answer. That one kind of looks similar to one that we did yesterday evening, right? Okay. Do another one here. We got a method called Festus. Let's see what's going on with Festus. Festus for the rest of us. F of 0. Seinfeld people out there. F of 0, okay. 0 is not greater than 6. Oh, interesting. So n becomes n times 2. 0 times 2 is still 0. I'm just going to write n as 0 here. That's not going to have anything to do with what it returns. I'm just keeping track of it. Return n, which is now still 0, plus Festus of 0 plus 1, which is 1. Interesting. I don't know what Festus of 1 is. Let's figure it out. Festus of 1. 1 is not greater than 6. N is currently 1. 1 times 2 is 2. So I'm going to do 2 plus Festus of 2 plus 1 is 3. You guys see where the 2 is coming from this multiplying by 2? Okay. Then I got to figure out what Festus of 3 is. I don't have to figure out what Festus of 2 is. Nobody's calling Festus of 2. I got to figure out what Festus of 3 is. 3 is not greater than 6. So n, which is currently 3, gets multiplied by 2 and becomes 6. So I'm going to return 6 plus Festus of 6 plus 1 is 7. I don't have to figure out what Festus of 4 or 5 or 6 is, but I do have to figure out Festus of 7 because it's been called right here. So Festus of 7 is, 7 is greater than 6. Huzzah! 7 minus 3 is 4, and then the fun begins. If Festus of 7 is 4, then Festus of 3 is 6 plus 4, which is 10. If Festus of 3 is 10, then Festus of 1 is 2 plus 10, which is 12. And if Festus of 1 is 12, then 0 plus 12 is, well, that's still 12. Good times. All right. Questions? All right. Today, we are going to write some recursive methods, but I need to get, we're actually going to do live coding today, something we haven't done in, I don't know, a long, long time. So I want you to go ahead and yeah, if you want, you could probably plug in your flash drives. Remember those? Oh, let me dust my flash drive off here. Don't blow on it. Make sure you cover your mouth when you blow on it. That's a joke. It doesn't. Yeah, make sure you use some hand sanitizer on your flash drives. No, don't do that either, please. Good gravy. We are gonna open JGrass. Sorry. Enough. My computer's got a virus quarantine. My computer's on self-quarantine. Oh, should I even touch it? Now you can trace the... Okay. It's like that movie Contagion. All right. Okay, here we go. Let's get a good old... Now, I don't know the person that's been on the computer if you moved seats. Here's how I recommend finding and opening JGrasp is if you hit that Windows key and just type in JGrasp. It should pop up, hopefully. Not JGraphs. Man. Okay. Okay. Matt, you still got internet? Great news. All right, yeah. Let's do a file new Java. Okay. I don't know what you want to call this. Maybe public class recursive methods. How about that? And something I haven't said in a while. It's a great time to compile and save. Here we go. I have not even made new folders. I don't even have an AP CSA 1 folder here, so just give me a second. Oh my gosh, it should be the new best class ever. Thank you for giving me a name here. AP CSA 1 new best ever. Yeah. I'm gonna talk smack to him. Okay, and we will need a main method at some point here. So if you've forgotten how to write a main method, still good news. You never have to write a main method on the AP test, so that's okay. But there it is if you've forgotten. It's been a minute. We've been doing all that CS Awesome where they give you the code. Too easy. Too easy. Alright. Get you guys started there. Okay. We're probably good on main method. All right, these are the steps for writing a recursive method. Now, I think I've said it before, probably like 99% of the time, recursion is not the way to solve a problem. But there are a lot of problems that you could solve with a loop or solve iteratively that you could solve recursively, and sometimes it is the right solution. And furthermore, you will have to know how to evaluate these at least. So that's what we're looking at today is writing recursive methods. Here are the steps. Step 1, I say begin by bailing out. When I'm talking about beginning by bailing out, basically start with write your base case first. Write base case first. Now that could mean a lot of things. It could be if the length of the string is 0, return 0. It could be a lot of different stuff. If you want to stop when an integer is -1, then you could say if it's -1, return 0, or something like that. But start with your base case. That should be like the first line of your method. Write your base case. Then, step 2, process. When I say process the first piece of data, another way you can think of it is process the current value. Or often that value is like the parameter that you're dealing with as well. So after you check for the base case, then if it's not the base case, deal with the value that you've been given. For example, if you want to do something, if it's even, then check if it's even before you do anything else. And then lastly, process the rest. In other words, do a recursive call and work your way to the base case. So as an example, if your base case says stop when an integer is negative, return something when an integer is negative, then maybe if the number's 5, you do something with the 5 and then you say return this method n-1. And so then you'll evaluate it with 4. And then you would return it with n-1 again with 3, and then n-1 again with 2, n-1 again with 1, then 0, and you're working your way towards that base case. If you don't work your way towards the base case, you're going to have infinite recursion, which is a total disaster. So again, number 1, start with your base case. Begin by bailing out. Number 2, process the current piece of data you have. Do whatever you're supposed to do with it. And then number 3, do a recursive call that works your way to the base case. Does that kind of make sense so far?
Yes.
Okay. Now we're going to write a couple different methods here. The first one is called isPalindrome. If you don't know what a palindrome is, it's the same string forwards and backwards, like race car is spelled the same way forwards and backwards. Mom, Bob, Dad, a man, a plan, a canal, Panama. Go hang a salami, I'm a lasagna hog. All of those are palindromes. Because they're spelled the same forwards and backwards. You can figure out if something is a palindrome recursively. And here's how you can do it. If the first character, and let me actually demonstrate it here on the side. I'll do it with race car. I'm going to write down race car. Not race card, race car. It's just, wait 1 second. All right, so considering if a string is a palindrome, it can be done recursively. First, check whether the first character and the last character of a string are equal. R and R are equal. Then what we want to do is, if they are equal, well, actually, if they're not equal, you're done. It's not a palindrome. But if they are equal, then ignore them. And now you have a new string, ace-ka. And now then you repeat the process. Are the first and last character the same? Yes, so ignore them. Now you're left with kek. Are the first and last characters the same? Yes, omit them. And then, if you are left with a string that is either length 0 or length 1, in other words, the length is less than or equal to 0, this means that it is a palindrome. So at that point, I'm left with E all alone. E itself is a palindrome. There's nothing else to check. At this point, I would return true. Now here is how you write it recursively. If we're trying to see if some string S is a palindrome. Step 1, begin with your base case. If the length is less than or equal to 1, return true. That is the base case. Stop there. So this is, I'm going to put a comment in here. Actually, I should use, what color? What color did I use? Green? Green. 1. Base case. So if the length of the string is currently 1 or less, return true. You're done. Bless you. Bless you. Step 2, process the first. Technically, we're processing the first and last characters here, but you want to process the current piece of data. So this part here, where I'm processing the current string, this is basically step 2. Process the first, or process the current is sometimes what I like to call it. Essentially, I'm checking that the first and last characters are equal to each other. And then if they are, I've got a recursive call here. This is 3, process the rest. Now, notice how I work my way down to the base case. My base case, again, is when the string's length is less than or equal to 1. What am I doing right here? When I call the recursive method again, what happens to S? It gets smaller. The first and last characters get chopped off. So I'm going to write down first and last characters are chopped off. That's how I'm working my way to the base case. Because you see that the substring starts at 1, that's going to be the second letter, and then it stops at the length -1, saying that's the first thing I don't want, means it chops off the last letter as well. So again, base case, process the first, and then process the rest. I'm going to go ahead and, if you want to type it out, you can. If you just want to click on the note sheet on the Google Classroom and copy it, that might be a wise decision as well. That's what I'm going to do. I know you folks are doing the same, not working on practice it. Oh, got him. Okay, let's go ahead and compile here, and okay. So I just copied it from the note sheet that's been posted virtually there. Posted, baby. It's on the classroom, right? Am I wrong? It's right. So right, it's wrong. Okay. So I just copied and pasted it there. I figure we could go ahead and, after I've got copied and... Now, I can't copy and paste in the main method. You guys know this. You can't write methods inside of methods. Are you out of your mind? You can call methods inside of methods, though. So that's what I'm going to do. Let's go ahead and maybe call it for... let's start with something simple like race car. Oh wait, I gotta call it. Is palindrome race car? Something like that. And if I run it says true, but that's not very interesting. I wanted to show you guys the tracing of it. Yeah. Okay, this might be a little complicated. Hold up. Where are you? Come here, baby. Okay. Race car. Okay. Step. Yeah, it's a palindrome. Okay, got it. And now look. Now it's ace car. Step. Now it's kek. Step. Now it's e. E's length is less than or equal to 1. So it's it returns true. And then if I were to try it with something that's not a palindrome, it'll eventually return false as it chops off letter by letter by letter there. So that's... go hang a salami, I'm a lasagna hog. Let's see here. Let's look at the recursive tracing here. Let's see. Go hang a salami, I'm a lasagna hog. Step through, it becomes, oh, hang a salami, I'm a lasagna, oh dear. Let's keep moving here. Hang a salami, I'm a lasagna. Let's keep going. Hang a salami, I'm a lasagna. A salami, I'm a lasagna. Gas a lami, mal asag. Asalami mialasa. Salami milas. Ala mi mala. Okay, Lamimal, Amima, Meme. I know these all sound like things Nintendo probably has in. Okay, and then I'm left with II. When I chop down II, I'm left with a length of 0 string, and it returns true, and we're done there. It's a palindrome, baby. Okay. Cool. Questions about this one? Here's my recommendation. If you have to write a palindromic method involving strings, my one recommendation for this is chop off characters using substring as you go. That's my recommendation. If you're dealing with strings, like we dealt with using substring to chop off the first and last characters. Wasn't there one? There was one on. There was one yesterday on CS Awesome, correct? There was the one that was looking for the Y's. Yeah. And so that's a similar thing. Chop off characters using substring as you go, so that you're working your way to the base case. And usually your base case is something that length is 0 or length is less than 2 or whatever. Questions here? 2-minute break. Go stretch your legs, get a drink of water, wash your hands, don't touch your face, stay 3 meters apart, you know the deal. All right. GCD, greatest common divisor. There is an algorithm called Euclid's algorithm that allows you to find the greatest common divisor between two numbers. In other words, the greatest number that goes into both of them evenly. Euclid's algorithm to find the greatest common divisor says the greatest common divisor of two positive integers is the largest integer that divides evenly into both of them. We can efficiently compute the GCD using the following property, which holds for positive integers p and q. If q is 0, then the greatest common divisor is p. If p is greater than q, then the GCD of p and q is the same as the GCD of q and p mod q. That sounds a little confusing. Let me kind of show how it works here. So let me demonstrate with the numbers here. 102 and 68. P is greater than Q, so then I'm going to find the GCD of 68 and P mod Q. What's 102 mod 68? Well, 68 goes into 102 one time. What's left over? 34? Yes. P is greater than Q, so I'm going to do the same thing again. I'll switch it so that P is Q. And then P mod Q, 68 mod 34. 34 goes in twice evenly with the remainder of 0. If Q is 0, return P. There is the GCD, 34. Between these two numbers, the GCD is 34. Now, if you want to ask me why this works, you're asking the wrong person. I'm not named Euclid. You'd have to ask Euclid, but it does work. So let's go ahead and copy and paste this bad boy into JGrasp here. And check it out. Check it out. Okay. So I'm just going to paste it before his palindrome. As long as you don't use the keyboard to clean up your sneezes, that would be... Okay. Here, I've got a hand sanitizer. Here comes $1 million worth of hand sanitizer. If that broke, I would destroy you. All right. Oh, look, now you get a little bit of hand sanitizer and you're feeling on top of the world. In a deluxe apartment in the sky over there. I see you. Okay. All right. Living it. I know. I should, yeah, that's my side job. Okay. All right. So let's try this GCD thing. I'm going to go ahead and call it with, well, let's start with the two numbers that we were given originally, which, of course, as a reminder, were 102 and 68. GCD 102, 68. Greatest common divisor is 34. Yes, that's true, but I want to see it actually doing the tracing. So I'm going to just show that to you guys really quick here. Using my using my handy dandy visualizer here in JGrasp. 68 and 34. 34 and 0, so at that point it returns 34. You can do this with any two numbers. For example, I don't know, 6,807 and 50.
How about 19 for COVID?
Oh, 19, a nice prime number for COVID-19. I don't know. Do they have a GCD? Their greatest common divisor is 1. No, but check it out. You can actually see the recursive trace going on here. That might be interesting for us. So I'm just going to demonstrate the recursive trace really quick. So then it becomes 19 and 5, 5 and 4, 4 and 1, 1 and 0. So that's why it returns 1 there, which I believe is probably true because 19 is a prime number. So that would not surprise me one bit there. So kind of an interesting algorithm. We should label the different parts here of this algorithm. We said first step, begin by bailing out, right? What did I make that? I made the base case red. So begin by bailing out. Here's your base case. That's step 1. When Q is 0, return P. That's your base case. Step 1. Now, it's a little bit tricky here to process the first and process the rest. It happens super duper quickly. I would say that you might say that this is processing the first. What color did I make that? Excuse me, 1 second. Blue. That's not good. Blue. You might say that this is processing the first. You might also say that this is processing the first because it's processing the current piece of data. Process the first or the current, if you want to say it like that. And then the last color I got here, this pink. Process the rest. This is definitely processing the rest here. Because look what happens with P mod Q. What am I guaranteed? The second thing, which represents Q, is going to be getting smaller, so I'm working my way towards the base case. So I do the base case, I process the first one if Q is 0, and then I process the rest by calling the method again and working my way towards the base case. Since the second parameter represents Q, as you can see, the second parameter is Q, and here we're doing P mod Q, which guarantees that value is going to be smaller next time, and smaller next time, and smaller next time. Often with integers, it's not modding, it's dividing, it's subtracting, something like that. So my tip for dealing with any primitives like doubles or ints or anything like that, work toward the base case by reducing the numeric variable. Typically, these base cases are when the integers or the doubles get super duper small, like less than 1 or less than or equal to 1 or less than 10 or something like that. So usually you're going to be either subtracting, you're going to be doing some division, or you might be doing some modding to the numeric variable to get it towards the base case. Does that kind of make sense? So with strings, you do substringing to cut it down. With integers and doubles, you're doing subtraction, division, modulus, etc. Questions there? All right. The last one. This last one with Matryoshka, maybe we'll look at it tomorrow. I'm just going to look at this arrays one to finish up here. Dealing with arrays. Counting the number of even numbers in an array could be completed iteratively, which means with a loop. But as we've seen in this lesson, many things completed iteratively could also be completed using recursion. To count the number of evens in an array, first of all, begin by bailing out. The way that we're going to say bailing out is if right here, this is our bailout. This is our step one. Essentially, if you hit the end of the array, stop. That's kind of our bailout. If you hit the end of the array, stop. Then process the first. Here's where I process the first. I say, this is step 2 right here. Essentially, if element at index is even, count it. Count it. And then step 3, my process the rest is really kind of in 2 spots, kind of here and here where I'm making my recursive call. My process the rest is call the method again with next index. So I'll demonstrate how this method works really quick, and then we'll run it. But it's common to do recursive stuff with arrays as well. And the way that you kind of make your array smaller, there's no way to substring an array. I think we've tried before to make arrays different sizes. You can do it with array lists, but you can't really do it with arrays. So what you do instead is you just keep passing the same array over and over again, but you keep track of the index as well. That's why there's 2 parameters here. And essentially my index variables keep going to get bigger and bigger and bigger and bigger and bigger until I get to the end of my array, and that's when I find my stopping point. So here's how this method works really quick. I'll just kind of draw a simple array and demonstrate it. Let's say that I've got 2, 3, 4, 5, 6, something like that. And I'll keep track of my index. So let's say I start at index 0 here. So what happens is, first of all, it goes, is index equal to the length of the array? No, the length of the array is 5. So then I check if the thing at index is even. The thing at index 0 is even, so I'm going to do 1 plus, and then I'm going to increment my index, like I've done here, index plus 1, and then I call it again. And so then I look at this guy. Is this guy even? Well, first of all, is index, which is currently 1, equal to the length of the array? No. Then is the element at index 1 even? No. So then I'm just going to return the method again, but I'm going to make the index bump up. So then I check at 2. Is this guy even? Yes, it is. So I'll add another one, and I'll call the method again. Index gets bumped up. Is this guy even? No. So index gets bumped up, and I call it again. 4 is not equal to 5. It checks if this guy is even. It is. Index gets bumped up to 5. 5 is equal to 5, the length of the array. So at that point it returns 0, and it goes all the way back and adds that on to the rest of these guys. 1 plus 1 plus 1 plus 0 is 3. There are 3 even numbers in that array. If you want to see it in action really quick, I'll just copy and paste it and show it to you. Boink, 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 boink. Here we go. Copy this guy. Paste it into the old JGrasper here. Maybe hit an F2 just to format it nicely. And I don't know. Actually, we could call it like this. Count evens. I want to send it this array here. 1, 2, 3, 4, 5. That's fine. And I'll have it start at index 0. Something like that. Two. And if you want to see what's going on, maybe I'll just run it with the debugger on for a moment here to show you. Get my array out as well. So it's starting at index 0. That one is not even. So then it does index 1. That one is even, so that would be 1 plus. Then at index 2, not even. Then at index 3 is even, so 1 plus 1. Then at index 4, not even. Then at index 5, it just returns 0, so 1 plus 1 plus 0 is 2. And that's the result there. So that's how you can find the number of evens in an array. Essentially, when you're dealing with arrays, you're not going to be able to chop them down like you could with substrings, or you're not going to be able to divide them or subtract them like you could with integers. So what do you do instead? You keep track of an index. And when that index either hits the end of the array, if you start at the beginning, or vice versa, then you can say I'm done with my method here. So my one tip with dealing with arrays in a recursive fashion, I would say keep track of the index as a parameter. Keep track of the index as a parameter, and then essentially when you hit the end of the array, you're done. I don't know. Done at length or something like that. So in each one of these, we've talked about how do you work your way to the end. With strings, you probably use substring to cut down. That's how you process the rest in your recursive call. With integers and doubles, you're probably doing subtraction or division or modulus to make them smaller in your recursive call. And then lastly, with arrays, you can keep track of the current index you're on, and when you get to the end of the array, you can say you're done. So it's all about process your base case and then work your way towards the base case using your recursive calls otherwise. Questions? All right. There is a minute assignment on Practice It. I think the self-check questions. So let me just demonstrate really quick on Practice It. I did put the link on the website. You want to make sure you're logged on. You do have a login because we've done problems on here before. You'll click on the chapter 12 questions, which are labeled as recursion, and there's kind of two different sections. There's a self-check section that starts out with self-check, and it says do 12.3. Well, 12.3 is just tracing a recursion thing here. 12, and then you do, when you finish that one, oh my gosh, why did I click on it like this? Wait, there's a 5th edition? Are the problems the same? Hold on. We've been doing them in the 5th edition. Maybe I just mislabeled it. Hold on. 12.3, 12.4, 12.5, 12.6. That's still the same. 12.13, 12.14, 12.15. That's still the same. 12.8, 12.9, 12.8, 12.9. We're good. This should just say 5. Sorry. If you started them in 4, that's okay. But sorry, they're the same problems. So the first couple, the self-checks, are just doing a little bit of tracing. I'll make a deal here. Pick out of these last 3, pick 2 out of the 3. All right. So if you want to do 12-8 and 12-9 and not 12-11, that's fine. If you want to do 12-8 and 12-11 and not 12-9, that's fine. If you want to do 12-9, 12-11, not 12-8, that's fine. The self-checks, these are just tracing. These last three are writing a recursive method. Is that an okay deal? Okay. All right, so I don't know how many that is. 3, 4, 5, 6, 13, 14, 15, 9 problems.
9 problems.
What? Yeah. So do them. Make sure you're logged in when you do them. I don't think I'll let you do them unless you are logged in when you do them. You could probably finish one right now, if not 2. You probably could if you're one of those people. Okay. Anyway, I don't know what tomorrow's gonna bring, but just I have a plan. I got plans. Just check. Unlike some other classes, our class is time sensitive because no matter what, May whatever AP test is happening. Luckily, we're ahead of the game. So just if anything ever happens, just check the Google Classroom. That's all I'll say. Okay? Okay.